Hi guys, welcome to the video where I teach you how to solve quadratic equations really fast. I will not use any factorization methods. They're commonly used, they're reliable, I know, but I want to use something even faster than factorizations. Okay, first step, we have to consider reduced quadratic equations. Reduced quadratic equations. Reduced means the leading coefficient is equal to 1. So in this quadratic equation of a standard form, ax squared plus bx plus c is equal to 0. This is a leading coefficient. A is a coefficient of x squared. It is equal to 1 in a reduced quadratic equation. So let's consider an example of x squared plus 5x minus 14 is equal to 0. So if you want to use a factorization method, we usually have to write something. I don't want to write anything. I want to give the solutions of the quadratic equation right away. This is an advantage of this method. So I developed 3 rules. First rule says that you guess the root, and candidates are divisors of the free term, of the constant term in the quadratic equation. Here it is. Minus 14 is a constant term in a quadratic equation. So let's list all the divisors. Minus 14 is divisible by, so this 3 dots means divisible by. So minus 14 is divisible by plus or minus 1, plus or minus 2, plus or minus 7, and finally plus or minus 14. So you can see 8 candidates. So there are 8 candidates. And we will try, not all of them, of course, but we start by considering the candidates from smaller to larger. So the second rule says that, it's my own invention. So look at the quadratic equation. There are 2 signs here, right? So this is the first sign and this is the second sign. So if the signs are the same, if the signs are the same, try negative candidates. So that is minus 1, minus 2, minus 7, and so on. And if the signs are not the same, or opposite. So this is exactly what we have in this example, plus, minus, they are opposite. If the signs are opposite, try positive candidates. So we will try plus 1, plus 2, plus 7, and so on. So I put x equals 1. So it mustn't take you a lot of time to calculate the value of the left-hand side and compare it with 0. That is 1 squared is 1, 5 times 1 is 5, so the sum is 6. 6 minus 14 isn't 0. So estimate rather than calculate, okay? So you have to be really fast here because the overall speed in this method depends on how quickly you can assess the results. You can estimate the results. So x equals 1 apparently doesn't work. What if x equals 2? 2 squared is 4. 5 times 2 is 10. So 4 and 10 is 14. Oh my God, exactly. It fits exactly. Minus 14 equals 0. So my first root is equal to 2. I guessed it. using the first two rules. Let me state the third rule. It comes from the relationship between the roots in the quadratic equation. It directly says that the product of the roots is equal to the free term. Oh, I used another term, constant term. Constant term divided by leading coefficient. Leading coefficient. But the leading coefficient is equal to 1. Yep, it's equal to 1. So that's why it's a constant term. It's equal to the constant term. So if the first root is already guessed, then the second root can be easily found by using this formula, constant term divided by the first root. Yep. So this is the easiest way to find the second root once the first root is already known. So let me go back. Here, the second root is constant term. Of course, it includes the sign in front of 14, because some people think that constant term is just 14. No, it's minus 14. You divide it by the first root. I usually draw an arrow like this. Minus 14 is divided by 2, so it's minus 7. That's it. The two roots are ready. So let's have some practice. So x squared plus 3x minus, let's say, 40 is equal to 0. The signs that are used in the quadratic equation are opposite again. So what are the candidates? What are the candidates? Minus 40 is divisible by plus or minus 1, plus or minus 2. Of course, when you're experienced enough, you will not produce this list of candidates, plus or minus 4, plus or minus 5, and so on. So I don't think I have to finish the list. So the signs in the quadratic equation are different, so they're opposite to each other. So I try positive candidates. 1, I know that x equals 1 is too small, right? It's too small. I will not even try to calculate the value of x squared plus 3x. I just know it's too small. Let's try x equals 2. I estimate rather than calculating. It's small, also small. 3, x equals 3 must be skipped because 3 isn't a multiple of 40. So I try x equals 4. Okay, 16 plus 12, no. 5. 5 is an ideal candidate because 5 squared is 25. 25 plus 15 is exactly 40. So the first root is 5. The second root is minus 40 divided by 5. It is minus 8. Yep. So the roots are ready. So you can ask me or ask yourself the significance of the second rule. Is genius because if you follow the rule number 2, it guarantees that the first root you will guess is smaller by its absolute value than the second root by its absolute value. So we consider the absolute values only. So it means that less number of candidates should be tried. So it's genius, rule number 2. Okay, let's try one more. So x squared, let's say minus 3x minus 28 is equal to 0. As you can see, the signs are the same now. It means I have to try negative candidates. So minus 28 is a constant term. The candidates are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 7, and so on. So I try negative candidates. So be careful with the signs of this negative 3. The coefficient of x is negative 3, but you try x as a negative number. So be careful with the signs. So -1 is too small. -2, it's too small again. -4, I think -4 is good. Yeah, because this is 16. -3 times -4 is 12. So 16 plus 12 is equal to 28. So the first root is nothing but -4. So, and this immediately allows me to find the second root by dividing -28 by -4. So the result is 7. So do you remember I mentioned the significance of the second rule? You see, the first root we guess is less by its absolute value, is less than the second root. So the second rule, do not ignore the second rule. Okay, so this was the first case of reduced quadratic equations, but as you probably have already mentioned, the nastiest and the most difficult quadratic equations are those with the leading coefficient being not equal to 1. Let's say 2x squared plus 5x plus 2 is equal to 0. So the leading coefficient, here it is, it's 2. It's a coefficient of x squared is not equal to 1. And we're not going to use factorization. I mentioned this in the beginning of the video. So the method I'm going to use is it's fantastic. Why it's fantastic? Because I take the leading coefficient and I move it by multiplying by the constant term. So 2, so it's no longer a leading coefficient. It goes to the constant term by multiplication. So it becomes x squared. So it's now 1. Yeah, of course, by default it's 1. But we write x squared plus 5x. It remains the same. And 2 is multiplied by 2. Of course, we take into account any signs they have. So plus 4. So 2 times 2 is 4 is equal to 0. And this is, let's call it auxiliary quadratic equation. So it's an equation of the type we have already considered. It's reduced quadratic equation. So we can apply the new knowledge we acquired in the part 1 of the video. So the two signs are both positive. They are the same. So I try negative candidates. So it's obvious for me. It's -1. So you can try like by putting it back into the quadratic equation, and it really fits. The second root is constant term divided by the first root. It's -4. But these are roots of the auxiliary quadratic equation. They are not the roots of the original quadratic equation. And to find them, I mean the roots of the original quadratic equation, we divide the roots of the auxiliary quadratic equation by this leading coefficient of the original quadratic equation. That is, I divide by 2. So -4 divided by 2 is -2. So these two numbers, this and this, are actually the roots of the original quadratic equation. Of course, I can't just show you the method without proving it. But let's try another example before we consider the proof, the strict mathematical proof. Let me show you 5x squared minus 16x plus 3 is equal to 0. Oh, even if you're good at factorization, so it will take some time. Of course, here I move 5 to 3. So it's x squared. So I multiply minus 16x plus 5 times 3 is 15 is equal to 0. So the signs inside the quadratic equation are opposite. So I try positive candidates. And the first root is obvious. It's 1. And the second root reveals itself automatically. It's 15 divided by 1. It's 15. But it was only an auxiliary quadratic equation. So if you're on the test and if you don't want to show this as a part of your solution, please write this uh, quadratic equation, auxiliary quadratic equation on the margins of your scratch paper or your exam list. So the roots of the original quadratic equation are 5 times less. So I divide by 5 here, I divide by 5 there. So it's, how much is it? Oh, 3. It's 3. So 1/5 and 3 are the roots of this quadratic equation. Okay, so as I promised, we have to consider the strict mathematical proof of the method. So it's relatively easy. Ax squared plus bx plus c is equal to 0. This is the original quadratic equation. And what are the roots of this quadratic equation? The first, second roots are, it's a famous formula, minus b plus or minus root of b squared minus 4ac, which is called discriminant, divided by 2a. Okay, this is the values that I expect at the end, because these these values are the roots of the original quadratic equation. But what we did seemed to be blasphemy. So we moved A to C, yeah? So, and the auxiliary quadratic equation we obtained, let me use the green color, auxiliary quadratic equation looks like x squared plus bx plus a times c is equal to 0. So the new leading coefficient is 1. The new constant term is ac. And here is the greatest idea this method is based on. When you write down the roots, so I start the upper part of the expression, it starts also by writing minus b plus or minus root of b squared minus 4. Then what we know, what goes next is leading coefficient, it's 1. And what goes next is the constant term, it's ac. Look, the discriminant is absolutely the same, despite the fact we moved the leading coefficient and we multiplied to the free term. The discriminant remained the same. And we divide by 2a, right? 2, but a now is 1. Yep, the leading coefficient is 1. So these are the roots of the auxiliary quadratic equation. So then, if you compare them with the roots of the original quadratic equation, you will see that the difference in this a that presents in the denominator. So these roots are guessed. Yeah, we just guessed the roots using the method in the first part of the video. And to get the roots of the original quadratic equation, we just have to divide them by a. Yeah, so we divide by a here, a rises here, and they become the roots of the original quadratic equation. So that's how it works. So one more example, I think one more example. 6x squared minus x minus 1, let's say, yeah, this one. So 6 goes to the free term, so x squared minus x minus 6 is equal to 0. So this is an auxiliary quadratic equation. I want to guess the roots. When you practice a lot you must be really fast. So it takes I don't know, 3 seconds, maybe no more than 5 seconds to guess the root. So this is -2. Of course, I took into account the signs of the quadratic equation. They were the same. So that's why I tried negative candidates, -2. The second root is -6 divided by -2. It's 3. But the roots of the original quadratic equation are 6 times less. So I divide each root by 6. Yep. So we can reduce the fractions -1/3 and 1/2. Yep. So that's it. That's it. Those roots are fractions. Okay. So I hope this video was useful for you. Subscribe and please feel free to ask questions in the comments section. See you.